Swayam Prabha. Digital India. Educated India.
Welcome to the class. Till time we had seen that if there is a flow through the nozzle, then how to estimate the velocity at the exit of the nozzle if it is a gas, or how to find out the mass flow rate through the nozzle. We have also seen the cases of choking of a nozzle. For that we had gone back and seen what do we mean by stagnation and total quantities. So now we are going to go ahead and see the impulse turbines from today's class. So here we have to first understand why nozzle flow has become important to us when we are interested to study the impulse turbine. We will see that, and also we will see how is it required for us to find out different performance parameters of a impulse turbine, or maybe down the line other turbine. So typical impulse turbine is this way, where we will have a nozzle. First the steam will be coming from boiler inside a nozzle, and then nozzle initially will have total enthalpy H naught at the entry of it, where we will have P naught as the pressure and T naught as the temperature. These things correspond to the boiler outlet, and then the flow expands inside the nozzle and attains very high velocity at the outlet of the nozzle. So at the expense of the enthalpy drop in the nozzle, we get increase in kinetic energy of the flow. So then this high velocity flow would impart its momentum on the blades. So these are the blades, and then due to imparting of this momentum, or due to interaction of the blade with the kinetic energy of the flow, this blade start rotating. So this is how we have a stage of an impulse turbine comprised of a nozzle and a moving blade. Nozzle is also called as a stator and moving blades are called as a rotor. So a stage is comprised of a stator and a rotor, or a nozzle and a blade. So this is typical condition in case of a impulse turbine. Since in case of impulse turbine we expect that whole enthalpy drop required for a stage will take place only in the nozzle. So nozzle or a stator is responsible for complete drop in enthalpy for a stage. However, there is no enthalpy drop going to take place in the blade. Accordingly, blades will not have any pressure drop taking place. So whole pressure drop will take place inside the nozzle, and no pressure drop will take place inside the rotor or the blades. Then this is a typical sketch where we will have flow coming from the nozzle, and then we are having blades. So these blades, when the flow comes, these blades will interact with the flow and then will divert the flow towards the outlet of the turbine. So this is inlet to the blades, this is outlet to the blade, and so flow is going to pass in between two blades. So in the case of impulse turbine, the flow will directly hit onto the blades, and then due to this interaction of the steam and the blade will try to rotate. Here we expect that while flowing through the passage of the blade, there is no enthalpy drop and no pressure drop for the blades. So this we are seeing actually a rotor ring in our slide. This is a picture of a rotor ring where we have this as the root and this as the tip, and then this is the height of the blade. So we have root diameter over here, we have tip diameter over here, and then we would have intermediate diameter. We have root diameter over here, we have tip diameter over here, but our analysis will mainly be focusing on mean height or mean diameter of the rotor. So practically, as what we have said earlier, we might have round nozzle or we might have foil nozzle. So in case of round nozzle, flow will go and hit the blades and then get diverted, and then due to which these rotor blades will rotate. In case of the foil nozzle, flow will be diverted by aerofoil, where this passage between the aerofoil would act as a nozzle, since it would have convergence, divergence or convergence and divergence section of the nozzle, and then it would impart its energy and momentum to the blades, which are moving blades, and then the blade will rotate. So this is the typical composition of a stage of an impulse turbine. Now this is how an impulse turbine would have its composition. So if we try to see, then we will have very low velocity at the entry to the nozzle. When the flow comes inside the nozzles, this is the nozzle, this is a nozzle section, and this is the moving blade. So this is the stator and this is the rotor. So we are seeing top view of this section for the rings. This is a stator ring, this is the rotor ring. So at the entry to the nozzle, we have very low velocity. This steam has come from the boiler. While flowing into the nozzle, velocity increases, and then between the rotor and the stator there is no change in velocity, but velocity decreases while flow is taking place inside the rotor or the moving blades. Similarly, whole pressure drop will take place inside the nozzle, and then there will not be any pressure drop taking place. Similarly, the case will happen for enthalpy. Whole enthalpy drop will take place inside the nozzle, and then there is no enthalpy drop which is taking place inside the moving blades, but this enthalpy is a static enthalpy. In case of total enthalpy, as what we know, total enthalpy is constant in the nozzle, and then total enthalpy will decrease into the moving blades. Since this is an isentropic flow without any work interaction inside the nozzle, we expect that there is no total enthalpy drop taking place in the nozzle, but there is work interaction, and due to work interaction we have basically enthalpy drop into the moving blades. So there is no total enthalpy drop inside the nozzle and also in the between the nozzle and moving blades, but there is total enthalpy drop inside the moving blades. Then let us see how to draw velocity diagram in case of the moving blades. So this is a typical section of a moving blade, and then this is a nozzle, and this nozzle is directing flow with absolute velocity V1. This is absolute velocity V1, but this velocity is making an angle alpha with the direction of velocity, which is rotation of the moving blade. So these moving blades are rotating in this direction. So this is the direction of velocity of the moving blades. So if rotor is moving with RPM n, then pi dn by 60 is Vb. So Vb is the rotor speed, and Vb can be said as pi dm into n by 60, and this Vb is the rotor speed, which is the tangential velocity at mean diameter of the rotor, where rotor is moving with n RPM. Then Vb is known to us. Since we can measure the n, we know the mean diameter of the rotor, so we know Vb. So this Vb and V1, which is absolute velocity, in between there is an angle of alpha. This is also called as nozzle angle or angle made by the absolute velocity. So knowing these two, we can find out the relative velocity at the inlet, which is VR1. So the angle made by VR1, which is relative velocity, which is rather tangential to the blade tip at the entry. So that angle is beta 1. Then flow will come out with relative velocity which is tangent to the tip of the blade with an angle beta 2 and magnitude VR2. But this is at the entry to the blade, this is at exit to the blade, but we are at the same height. So we are at same dm. Basically, if we go back and see, so we are trying to do analysis on this plane. We are trying to do analysis on this plane. So in this plane we are trying to do inlet velocity triangle here and outlet velocity triangle here. So we are on the same plane, and since we are on the same plane, we are having same VB which is existing at the inlet. So we will draw same VB, and this beta 2 is the angle made by VR2 with VB. Then knowing these two velocities, we can find out the resultant, which is absolute velocity V2 at the exit of the blade. So this is the inlet velocity triangle and this is outlet velocity triangle. So now these two triangles we can combine with each other, since both the triangles have same base, which is VB. So this is VB. Now we know inlet velocity triangle. So for the inlet velocity triangle, we have this as V1, this as V1, this as VR1. So this is alpha, this is beta 1. Then we have parallelly drawn outlet velocity triangle over here, where we have this as V2 and this as VR2, where absolute velocity is making angle delta, and then we have beta 2 angle made by the relative velocity with VB. Here we have two things which can happen. This absolute velocity is going with an angle delta which is more than 90 degree, or maybe an angle which is less than 90 degree. So accordingly, this point will laterally move somewhere. So if it is less than 90, then it will come inside. If it is much more than 90, then it will go on that side. So this is one more demonstration where V2 is making an angle which is less than 90. Rest of the things are similar. Then we are more interested in something else, that we will say that here we are interested in finding out the torque or the power output. So for finding out torque, we are more interested in the change in angular momentum of the stream of steam which is coming and leaving the rotor. So there is some velocity which is angular velocity Vw1 at the entry to the blade, but that angular velocity will get reduced to Vw2 at the outlet. So the difference in angular velocity is delta Vw for the steam, and this change in angular velocity is responsible for creating the torque. So if we are having the angle more than 90 degree, then change in Vw is basically summation of Vw1 and Vw2. But if we have an angle which is less than 90 for absolute velocity, then Vw1 will be bigger than Vw2, and then their directions are opposite. So delta Vw is Vw1 minus Vw2. So this is what we should also remember. So knowing these things, we can go ahead and do further analysis for the velocity triangle. So there is one more thing to be noted over here, that we are having axial velocity. This absolute velocity V1 can be split into two parts. One is 90 degree part and one is tangential part. So this tangential part is Vw1, which is angular velocity, and then Va1 is axial velocity. Basically Va1 is responsible for the axial motion of the fluid along the axis of the rotor, and Vw1 is responsible for the angular momentum of the rotor. So, but it might happen that we might have change in axial velocity. So, this change in axial velocity leads to basically decrement in axial velocity, and this decrement is delta Va. So, the outlet will have lesser axial velocity than the inlet. This would happen due to wobbling of the rotor or due to axial thrust of the rotor. We know that if there is when the fluid of water goes or steam goes from the rotor blade, then they are going to impart the momentum such that it will rotate. So, the stream will rotate, but while rotating, if the rotor blade makes this motion, then it is called as axial thrust imposed by the steam, and then that axial thrust is basically leading to decrease in axial momentum. So, this is change in axial momentum, or for the constant mass flow rate, this is change in axial velocity. So, this is what we have to find out. Then we have to find out all these parameters. So, let us say that we are interested in finding out initially the tangential thrust. So, tangential thrust or torque applied by the mass of steam which is going through the rotor is mass flow rate into change in angular velocity, which is necessarily change in angular momentum. So, torque is actually change in angular momentum, which is mass flow rate into change in angular velocity. So, we will denote it by Pt, which is tangential thrust or torque. So, we have it is so Pt is equal to mass flow rate m dot into delta Vw. Similarly, Pa, which is axial thrust, and that is equal to m dot, which is mass flow rate into delta Va. So, these two things we need to evaluate. So, for this evaluation, essentially for the simplified analysis, we would generally consider that there is no axial thrust, but we are more interested in finding out power produced. So, we are more interested in finding out delta Vw and Pt. So, let us consider the inlet velocity triangle. From inlet velocity triangle, we can see that V1 cos alpha minus Vb is equal to Vr1 cos beta 1. We are trying to say that V1 cos alpha is Vw1, V1 cos alpha is necessarily Vw1, and Vw1 minus Vb is equal to this portion, is this portion. So, this is Vw1 and this is Vb. So, Vw1 and so this is Vb. This is Vb and this is Vw1. So, Vw1 is equal to, so basically V1 cos alpha. So, Vw1 minus Vb is this part, and this part is Vr1 cos beta 1. So, knowing this, we similarly can write, so we can say it as Vw1. Similarly, Va1 can be written as V1 sin alpha, but that is also is equal to VR1 sin beta 1. So, we will consider this as equation number 1 and equation number 2. So, let us divide equation number 1, equation number 2 by equation number 1. So, divide 2 by 1, and then we will get tan of beta 1 is equal to V1 sin alpha divided by V1 cos alpha minus Vb. So, this is our formula for finding out beta 1. Since V1 would be known to us, and for that we have seen how to find out V1 based upon nozzle efficiency and enthalpy drop. So, we will be knowing V1. Alpha is the nozzle angle which is based upon the setting of the nozzle. So, alpha also will be known to us. Vb is pi dn by 60. So, that is based upon the RPM measurement. So, we would know all the right hand side quantities. So, then we can calculate beta 1. So, this leads to beta 1 is equal to tan inverse of V1 sin alpha divided by V1 cos alpha minus Vb. Then we can go to the exit velocity triangle. So, for the exit velocity triangle, we can similarly write down that V2 cos of 180 minus delta, 180 minus delta is this, and then that is V2 is this, cos delta is this distance, which is VW2. So, VW2 is V2 cos of 180 minus delta plus Vb, and Vb is this, and that is equal to VR2 cos of 180 minus gamma. So, gamma is this angle, 180 minus gamma is this angle, which is necessarily beta 1, VR1 cos of beta 1. Okay. So, having said this, we can also write down the same thing by one more way, where we have minus V2 cos of delta plus Vb is equal to minus VR2 cos of gamma. So, we can write down it as V2 cos of delta is equal to VR2 cos of gamma plus Vb. So, this is our equation number 3. Now, we have to make certain assumption about the friction in the moving blades while the flow is taking place. So, due to friction, the relative velocity will decrease. So, VR2 upon VR1 is said to be as Kb, where Kb is a blade friction factor. So, this Kb would be our interest to be known for estimating the different performance parameters of the impulse turbine, since there is loss in kinetic energy of the flow due to friction, and that is VR1 square minus VR1 square minus VR2 square divided by 2. This is per kg second. So, this is what the loss in kinetic energy or power due to the friction inside the blades. So, now we have told that we are interested in finding out delta VW. So, delta VW is equal to VW1 which is rather from this velocity triangle VW1 plus VW2. So delta VW is equal to V1 cos of alpha minus V2 cos of delta. V2 cos of delta. This is what we had seen, VW1 minus VW2, VW1 minus VW2. So this is VW2. So here this is what we have derived, VW2, VW2. So VW1 minus VW2 is delta VW, and then this delta angle will take care of the sign. So VW1 minus VW2, if V delta is more than 90, then this will automatically become positive. If delta is less than 90, this will become negative. So this is taken care by the signature of sign of delta. So delta VW will be V1 cos of alpha minus, we know now from equation 3, V2 cos delta is equal to VR2 cos of gamma plus VB. So we have delta VW is equal to V1 cos alpha minus VB, we will make a bracket to this, minus VR2 cos of gamma. But considering the blade friction coefficient, we can write VW is equal to V1 cos alpha minus VB minus KB into VR1 into cos of gamma. So we can write down this further, since we can know what is VR1, and VR1 can be found out from this expression, which says that VR1 from equation number 1 we can get VR1 is equal to V1 cos alpha minus VB divided by cos of beta 1. So this is the expression for VR1 from equation number 1. So this expression we can put over here and say delta VW is equal to V1 cos alpha minus VB minus KB into cos gamma into V1 cos alpha minus VB divided by cos of beta 1. So then we have delta VW V1 cos alpha minus VB as common, and then we would have 1 minus KB into cos of gamma divided by cos of beta 1. So this is what we would have as an outcome of delta VW. But we have seen that cos of 180 minus cos of gamma, but we know that gamma is equal to 180 minus beta 1. So cos gamma is equal to cos of 180 minus beta 1. So we will have this here, will have minus sign. So we will have this, okay, this is not minus sign, so no problem. So this is cos of 180 cos gamma is equal to minus cos of beta 1. So this, if we put delta VW is equal to V1 cos alpha minus VB into 1 plus KB into cos of beta 1 divided by cos of beta 1. So we will have delta VW is equal to V1 cos alpha minus VB is equal to 1 plus KB. So this is the expression for our change in angular velocity. So now using this expression we can find out what is the PT. So PT is equal to mass flow rate into delta VW. So PT in case of per kg of steam flow rate, we will have it is equal to only delta VW, but let us consider with delta VW or with mass flow rate, then it is delta VW. So m dot into V1 cos alpha minus VB into 1 plus Kb. This is our tangential thrust, or this is our torque. Now this, if we want to measure in terms of power, so we will have power is equal to m dot into V1 cos alpha minus VB 1 plus Kb into VB. So this is the power output of the turbine. In case of frictionless flow, then Kb is equal to 0, then we will have power is equal to m dot V1 cos alpha minus VB into VB. So this is for frictionless flow. Similarly, we will have PA, which is m dot into delta VA, and delta VA is equal to m dot into VR1 sin beta 1. VR1 sin beta 1 is VA1 minus VR2 sin of beta 2, which is the small VA2. So then again PA is equal to m dot, we can take VR1 common, so we will have VR1, then we have sin beta 1 minus VR2 upon VR1 into sin of beta 2. So we have axial thrust is equal to m dot VR1 sin beta 1 minus Kb into sin beta 2. So if we take sin beta 1 also common, then m dot VR1 sin of beta 1 1 minus Kb into sin beta 2 upon sin beta 1. When the blades are said to be symmetric blades will have beta 1 is equal to beta 2. So then this would get cancelled, and for symmetric blades PA is equal to m dot VR1 sin beta 1 into 1 minus Kb, that is only for symmetric blades. Okay, so knowing this, we can go ahead and derive the next part. So we will go and derive an expression for efficiency of the blades. So that is called as blading efficiency. So let us derive the expression for blading efficiency, which is also called as diagram efficiency. Then how to find out diagram efficiency, or what is definition? It is said that diagram efficiency is equal to rate of work done on blades divided by rate of energy input to blades. So knowing this, we know that basically this is work done, and that work done is m dot into delta VW into VB, and this energy supplied is 1/2 m dot into V1 square. So this becomes twice delta VW into VB divided by V1. But we have already found out what is delta VW, so we can put that and say this as equal to 2 into V1 cos alpha minus VB into 1 plus KB into VB divided by V1 square. So we will have it as, if we take VB as common from this bracket, then if the diagram efficiency is equal to 2 into 1 VB is common from this bracket, then this bracket will become V1 upon VB into cos alpha minus 1 into 1 plus KB into this VB as it is divided by V1 square. So this term can also be written as 2 VB square into V1 upon VB into cos alpha minus 1 into 1 plus KB divided by V1 square. Let us say that VB upon V1 is equal to rho, and this is called as velocity ratio. So this expression we can write down as diagram efficiency is equal to twice this VB square, and this V1 square will constitute rho square into cos alpha upon rho minus 1 into 1 plus KB. So this is our basic formula for diagram efficiency, which has rho or velocity ratio in it. Now it is clear that for a frictionless blade it is just function of alpha and rho, but alpha is our setting from the nozzle angle, so mainly it depends upon rho. So let us differentiate this diagram efficiency with respect to rho, and then we can get here as equal to 2 into, we can first do this d by d rho of, we will multiply it here, so we have twice rho cos alpha minus rho square minus twice rho square into 1 plus KB, and then we can differentiate d by d rho diagram efficiency is equal to 2 into cos alpha minus 2 rho into 1 plus KB. So this leads to the fact that for an optimum condition of rho, this should be equal to 0 for optimum condition. So at the optimum condition we will have 2 into cos alpha minus 2 rho into 1 plus KB equal to 0. So this leads to the fact that we will have rho is equal to, now we will assume that KB, let us say that KB is equal to 0 for frictionless blades. So we will have 2 into cos alpha minus 2 rho is equal to 0, and this leads to rho is equal to cos of alpha by 2. So, this is called as rho optimum. So, diagram efficiency can be written as 2 rho optimum square into cos alpha upon rho optimum minus 1. So, this can be further obtained as diagram efficiency. If we put rho optimum as cos alpha by 2, then we can get further this kb being a constant, we can as well have this getting divided, since this is a constant. So, we will not have this to be appearing. So, if at all kb is 0 and if at all kb is not 0, we will have rho optimum is equal to cos alpha by 2, since this can be going on that side since kb is a constant. So, rho optimum, so that is why we will also have 1 plus kb in a general case. So, we will have diagram efficiency is equal to cos square alpha by 2 into 1 plus kb. So, this is our expression for diagram efficiency, and this for frictionless blades become diagram efficiency is equal to cos square alpha by 2 for an impulse turbine frictionless case. Okay. In general, alpha is kept in the range of 16 to 22 degrees. So, that is where we can know what would be the optimum case, optimum efficiency of the blades. So, here we have done the derivation for the case of impulse turbine. We will see that instead of drawing or deriving this expression or calculating it to the measurement, we can draw this velocity diagram on our own. Here in this case we know V1 from the enthalpy drop in the nozzle efficiency, we know V1. So, and further we also know Vb, which is pi dn by 60. So, two absolute magnitudes of V1 and Vb are known. We know alpha and kb, two quantities are known to us. So, what we would do is we will first draw line V1 and line Vb with an angle alpha in between them, where we would take a scale as 1 centimeter is equal to some x amount of meter per second. So, we know V1, so we will scale it down. We know Vb, so we will scale it down. First we will draw Vb as a horizontal line up to the scale, then we will make second line with the angle alpha, and on that we will make V1 magnitude. So, then we will find out this point C. Knowing the point C, we can connect it with point A, and then VR1 will be known to us. Further, we know that there is an amount which is kb. So, from that we can know VR2, and we also know the blades are symmetric. So, we know beta 1 and beta 2. So, then once we know beta 2, we will draw second line and we will reduce VR2 by an magnitude which is factor by kb. So, we would have find out point E. Then we can connect point E with V2 or point B and then found out V2, and thus we would have completed our velocity triangles. Then knowing this, we would have measured delta VW multiplied by scale, and then we could get the power or torque from this graphical representation instead of the geometrical calculations from the velocity triangle. So, we had seen how to work out for an impulse turbine by graphical representation and also by geometrical means and find out efficiency and torque. We will see rest of the part in the next class. Thank you.